Assalamu alaikum students. Jamil is here from Department of Biochemistry, FRPMC. Our topic is enzyme kinetics, in which we will study the chemical reactions catalyzed by enzymes and their rates under varying conditions or different conditions. Learning outcomes. After this discussion on the topic of enzyme kinetics, you would be able to define enzyme kinetics, know its biomedical importance. You will study briefly the mechanism of action of enzymes, which has already been taught to you. You will understand Michaelis-Menton model of enzyme kinetics and Lineweaver Burk plot, and in the last you would be in a position to explain significance of Km and Vmax. Enzyme kinetics is the study of chemical reactions which are catalyzed by the enzymes. In this, the rate of reaction or speed of the reaction or the velocity of the reaction is measured quantitatively, and we also investigate the varying conditions or factors affecting the reaction rate. Biomedical importance of enzyme kinetics. The enzymes are very much important biomolecules, so that if there is no enzyme, there is no life. The study of enzyme kinetics reveals the catalytic mechanism of that enzyme, its role in metabolism, its activity, and how a drug or agonist might inhibit the enzyme. Physiological stresses such as anoxia, metabolic acidosis, alkalosis, toxin, and drugs, they affect the homeostasis. The understanding of this homeostasis is very much important, and enzyme kinetics has the fundamental role in understanding of the maintenance of that balance. Kinetic analysis can reveal number or steps and order of the enzyme catalytic reactions. Order of kinetic, first order, say for example, or zero order. The kinetic analysis plays a critical and central role in drug discovery, comparative pharmacodynamics, that is mechanism of action of drugs, and how these drugs act or inhibit the enzyme activity, or how they affect the enzyme activity. You have the clear concept about the mechanism of action of enzymes. Just we'll go an overview to recall as a ready reference. Mechanism of action of enzymes we study in two perspectives. Catalyst in terms of energy, that is energy change, and second perspective is catalysis in terms of binding of substrate on the active side of the enzyme. The first perspective, that is change in energy during the process of chemical reaction catalyzed by enzymes. What the enzymes do? Enzymes, they lower the free energy of activation. And what is the free energy of activation? It is the energy difference between the reactants and a high energy intermediate that occurs during the formation of product, which is called transition state. It is not the energy difference between the reactant and products. It is energy difference between reactants and transition state. While difference between reactant and product, difference of energy between reactant and product is denoted as delta G, that is energy difference. When enzymes lower the free energy of activation, so molecules of the reactant have more energy or sufficient energy to pass through the transition state, and thus they faster the rate of reaction or the speed of reaction. It is the pictorial view how enzymes affect free energy of activation of a chemical reaction catalyzed by them. A is the substrate, B is the product, and halfway between the two is the transition state, a high energy intermediate. The chemical reactions catalyzed by enzymes, they proceed via this transition state. On this graph, free energy is plotted on y-axis and speed or rate of reaction or progress of reaction on the x-axis. Here is the substrate A and it is the B product. Substrate has energy level. Here is the energy level of the substrate or reactant, and the product also has a energy level. Substrates or reactants, they have high energy than the product. So difference between energy of substrate and product, the magnitude is shown here and it is denoted by delta G. But what happens practically when substrate is converted into product? It attains high energy to be reacted more and more, and it attains a transition state having high energy, and then reactions are possible and product is formed. A acquire a higher level of energy when uncatalyzed, but when catalyst is there, they also acquire the transition state, but here they get the transition state, and you see that less energy is required to be converted substrate or reactant into transition state and then finally converted into product. So this magnitude or this arrow, red arrow, is showing free energy of activation catalyzed by enzymes. This is decreased. If uncatalyzed by enzymes, then it could be of this much, having high value. But enzyme catalyzed reaction, it decreases. So enzymes, when they catalyze the reaction and convert substrate into product, this free energy of activation is decreased. This decrease in free energy of activation is sufficient to maximize the rate of reaction and substrate is converted into product. So here is the difference of free energy of activation. That is difference between uncatalyzed and catalyzed reaction. Difference of energy between uncatalyzed and catalyzed reaction. The catalysts, they decrease the free energy of activation. So more and more substrate molecules are converted into product, and because less energy is required. The same number of molecules, if converted in uncatalyzed reaction, they will require high energy of activation. But this high energy of activation is decreased in the reactions when the reactions are catalyzed by the enzymes. One thing more important, that delta G, that energy difference between substrate and product, doesn't change, whether uncatalyzed by a catalyst or catalyzed by the enzyme. So difference of energy between reactant or substrate and product is the same, but free energy of activation in uncatalyzed and catalyzed reaction has a difference. Free energy of activation required in uncatalyzed reactions is more, while the free energy of activation in catalyzed reactions catalyzed by the enzyme is less. Because of this decrease in free energy of activation, the progress of reaction is speeded and proceeds toward the right side. The second perspective of the mechanism is when enzyme binds with the substrate, it makes enzyme substrate complex. This enzyme substrate complex stabilizes the high energy intermediate transition state T. When more and more concentration of high energy reactive intermediate is formed, they are converted to the product and thus accelerate the reaction. So formation of enzyme substrate complex, that is enzyme with substrate on its active side of the enzyme, resulting ES complex, stabilizes or promotes the transition state. In the transition state, where free energy of activation is decreased, more and more molecules they react and be converted into product. So this perspective is that, second perspective is that enzyme substrate complex, it stabilizes or increases or promotes the transition state. A third perspective is also there, and it is proposed that enzymes, they channel the substrate molecules to the metabolic pathway, especially in those reactions which are energetically favorable. Some reactions are energetically favorable and they can proceed spontaneously. And those energetically favorable or spontaneous reactions, the enzymes, they channelize the substrate molecules in the metabolic pathway. But the concept of transition state, that is high energy transition state, this concept or the role of transition state was suggested by Linus Pauling, Nobel laureate Linus Pauling. The mechanism of action of enzymes, generally what happens, the energy catalyzed reactions or enzyme catalyzed reactions, they proceed from 10 raised to power 3 to 10 raised to power 8 times faster than the uncatalyzed reactions. This fasting rate of reaction is just by virtue of presence of the catalysis in the form of enzymes or biocatalysts. Different models were proposed for enzyme kinetic analysis, having different substrates, more than one substrate, more enzymes or multiple enzymes. But the study of those models are beyond the scope. So we will study the MichaelisMenton model. It was proposed by Leonard Michaelis and Maude Menton. It is the simplest and best known model. Account for the most of the features of enzyme catalyzed reactions. Michaelis and Menton described how rate of reaction varies with substrate concentration. The substrate concentration is one of the first things that is measured in enzyme kinetic analysis. Michaelis and Menton performed few experiments on the chemical reactions catalyzed by enzymes and concluded some observations and derived a mathematical equation. Later on, that were modified by the Lineweaver and Burk in the form of a plot. Let us see what is Michaelis-Menton equation and how it helps to understand enzyme kinetics. It is a mathematical kinetic analysis of enzymes which studies or spheres around variation in the rate of reaction, variation in the speed with the changes in substrate concentration. The experimental reaction model involves one enzyme and one substrate. One enzyme and one substrate model, when they react, they are converted into enzyme substrate complex. But they also propose this reaction as a reversible reaction having different rate constants. Enzyme substrate complex is then energetically converted into enzyme and product having another rate constant. S is the substrate, E is the enzyme, ES is the complex, and P is the product. While K1, K2, and K-1 are rate constants. K1 is the rate constant for the formation of ES complex. K-1 is the rate constant for the dissociation of enzyme substrate into enzyme and substrate, that is reverse reaction. While K2 is the rate constant for the dissociation of enzyme substrate complex into enzyme and product. Here is the presentation how enzyme, its active site combines with the substrate. One enzyme, one substrate. Enzyme substrate complex is formed. This is converted into enzyme product complex. In between there is a transition state, and this is converted into product, leaving active site of enzyme, that is, enzyme is retrieved in the original form. Equation describes how reaction velocity or rate of reaction varies with the changes in substrate concentration. He derived mathematically. This is the final equation. The derivation of this equation is cumbersome and lengthy and beyond the scope of the syllabus. So only I am showing the final form of equation. V naught is equal to V max multiplied by substrate concentration divided by Km minus Michaelis constant plus substrate concentration. This is the equation governing the kinetics of Michaelis-Menten equation. Here V naught is initial reaction velocity, V max is the maximal velocity, Km is the Michaelis constant, S is the substrate concentration. This equation is based on some presumptions and experimental conclusions, but derived mathematically by Michaelis and Menten. What were those presumed conditions? That this equation or equation stands for one substrate, one enzyme type of catalyzed reactions. The substrates are of one type, not more than one. The enzymes are of one type, not the multiple enzyme system. Second presumption, the concentration of substrate is much greater than the concentration of enzyme, so that substrate is not exhausted, it is always present. This is a chemical reaction which acquires a steady state where complete formation of substrate into product is there. Enzyme is released and retrieved in the original form. Complete utilization of substrate bound with the enzyme into product. These are the important conclusions drawn from Michaelis-Menten model of kinetics. Km is the characteristic of enzyme to its particular substrate, and numerically it is equal to substrate concentration when half of the maximum velocity is achieved. So numerically Km is equal to the substrate concentration at which half Vmax is achieved. This shows 50% saturation of the enzyme, giving you half of the maximum velocity. When half of the Vmax is achieved, at that time, what could be the substrate concentration? That would be equal to Km, particular for that enzyme and its particular substrate. Km does not vary with the enzyme concentration. When we increase the enzyme concentration, it doesn't affect the Km. And it shows the affinity of the enzyme for its particular substrate. A small or low Km reflects a high affinity of the enzyme for its substrate. Enzyme having high affinity for particular substrate, that means low concentration of substrates are required to saturate 50% of enzyme. So small or low substrate concentrations or small or low Km reflects a high affinity of enzyme. Large or high Km values reflect a low affinity of enzyme for substrate. That is, when half Vmax have to be achieved, a larger concentration of substrate is required to achieve 50% saturation of enzyme to get half Vmax. They also concluded the effect of enzyme concentration and substrate concentration on the rate of reaction or velocity of the reaction catalyzed by the enzymes. The rate of reaction is directly proportionate to the enzyme concentration at all substrate concentration. Substrate concentration, whatever may be the substrate concentration, whenever we will increase the enzyme concentration in the reaction, the velocity or the rate of reaction will be enhanced. So the rate of reaction is directly proportionate with the enzyme concentration at all substrate concentrations. The effect of substrate on the rate of reaction follows two orders: first order and zero order of kinetics. When concentration of substrate is much less than the Km, that is the concentration of the substrate at which half of the Vmax is achieved, when substrate concentration is lesser than the Km, much less than the Km, the rate of reaction or velocity follows the first order. That when we increase the substrate concentration, the rate of reaction will be increased. Zero order, when substrate is much greater than the Km, the rate of reaction becomes independent. It doesn't change with the further increase in substrate concentration. So when substrate is much more than the Km, the rate of reaction becomes independent and follows the zero order of kinetics. It is graphical presentation to analyze the effect of substrate concentration on the reaction velocity. Substrate concentration on x-axis and reaction velocity on y-axis. You see the Km. Km is the substrate concentration where the half Vmax is achieved. That substrate concentration which gives you half of the maximum velocity is the Km, Michaelis constant. And it is the characteristic of that enzyme. And it is a constant. When half Vmax is achieved, on that the concentration of substrate is equal to the Km. When there is at low concentrations of substrate, that is when the substrate concentration is much less than the Km, the order of the reaction is first order of kinetics. It is proportionate. Velocity increases with the increase in substrate concentration. But since the plot is hyperbolic, it is not the straight line, it is hyperbolic. So at high concentrations of the substrate, that is when substrate is much greater than Km, the velocity of the reaction is of zero order. That is, it is independent of substrate concentration. We keep on increasing the substrate concentration, the rate of the effect of substrate concentration on the velocity is following zero order, a hyperbolic curve. This point going for the straight line is the point where there is a complete saturation of enzymes by the substrate. So practically Vmax is not achieved. We can reach to the Vmax by increasing the substrate concentration, but we cannot achieve the Vmax because before that the complete saturation of enzyme by the substrate is there. So initially it follows first order when substrate concentration is much less than the Km, but if the substrate concentration is much greater than the Km, the order becomes of zero, creating a hyperbolic curve. Lineweaver-Burk plot. Lineweaver-Burk plot utilize the hyperbolic curve of the equation and converted it into a linear form by taking double reciprocal of the quantities, that is velocity and substrate concentration. So this linear form, when we reciprocated the velocity quantity and the quantity of the substrate, a linear form of plot was obtained named as Lineweaver-Burk plot. It is useful to calculate the Km and Vmax. Vmax cannot be calculated in Michaelis-Menton plot, but in this plot we can calculate Vmax, though achieved or not achieved. But this is also helpful to determine the mechanism of action of enzyme inhibitors. The enzymes are inhibited by many drugs, and you will appreciate the linear form of Michaelis-Menton equation helping in understanding of mechanism of action of enzyme inhibitors. Lineweaver and Burk, they studied the Michaelis-Menton model of enzyme kinetics, and they developed another equation and plot by taking the reciprocal quantities, the velocity in its reciprocated term and substrate concentration on x-axis in its reciprocated term, which resulted a straight line. This straight line is more helpful to understand the enzyme kinetics. The derived equation stands 1 upon initial velocity is equal to Km divided by Vmax multiplied by substrate concentration plus 1 upon Vmax. The derivation is also important, but it is not included because of the scope. If we come to the plot, Lineweaver-Burk plot, this straight line resulted because of the 1 upon S and 1 upon V, the reciprocated terms. The intercept on the y-axis is reciprocal of the Vmax. The intercept on the x-axis is the reciprocal of the Km, minus sign showing the shift on the left side of the graph, left side of the x-axis. beyond the zero. And this plot and equation is helpful in calculating the Vmax because of the linear shape of the plot, while that is not possible in the Michaelis and Menten plot, which is hyperbolic in shape. This plot is also helpful in understanding the mechanism of enzyme inhibitors, which we will study in the next lecture. It also shows the relationship of the Km with the Vmax in the form of a slope. This is a slope. If we take part of the slope and draw a right angled triangle, the hypotenuse, that is the slope, is equal to Km divided by Vmax. So what are the advantages of the Lineweaver-Burk plot is that numerically Vmax can be calculated, though practically not achieved, and we can understand the mechanism of action of enzyme inhibitors, and we can also calculate the slope. Significance of Km and Vmax in enzyme kinetics. Michaelis constant, or Km, reflects how much enzyme is active or how much affinity an enzyme shows towards its substrate. The Km numerically is equal to the substrate concentration at which half maximum velocity of the reaction is observed. Km implies that half of the active sites on the enzyme are filled. When half of the active sites are filled, it gives half of the maximum velocity, and that half maximum velocity is achieved by certain substrate concentration which is equal to the Km. It is the measure of binding strength between substrate and the enzyme. Small Km values indicate a high affinity of the enzyme for the substrate, while high Km values indicate low affinity of the enzyme for its particular substrate. Vmax is the maximum velocity of the reaction or reaction rate at which the enzyme catalyzed a reaction under given conditions. Or we can say it is the maximum capacity of an enzyme, how much substrate it can consume and convert them into product. Vmax is reached when all enzyme sites are saturated with the substrate. And this will happen when substrate concentration is much greater than the Km. When substrate concentration is much greater than the complete or full active sites of the enzyme can be occupied by the substrate, giving you the Vmax. Both have significance for a particular enzyme. Both Km and Vmax are constant for a particular enzyme under constant given conditions. The whole discussion is summarized in the form of a map. On the left side, the enzymes, their properties and mechanism of action is represented in the form of blocks. On the right side, the enzyme kinetics is reflected. Michaelis-Menton equation, factors affecting the Michaelis-Menton equation, and plot, first order and zero order in the plot and other things made easy for you to memorize. This key concept map is taken from the Lippincott. Here is my mailing address, and recommend resource is Lippincott's Illustrated Review, 7th edition. Thank you.